Hi everyone, in this video we are going to discuss about support vector machine algorithm. This video is a part of an introduction to classification series. If you want to refer the complete playlist, I will provide the link in the description. Now let's get bang on to it. What is SVM? Support vector machine are a type of supervised machine learning algorithm that provides analysis of data for classification and regression. While they can be used for regression, SVM is mostly used for classification. The goal of the SVM is to create the best line or decision boundary that can segregate n-dimensional space into classes so that we can easily put the new data point in the correct category in the future. This decision boundary is called a hyperplane. The dimension of the hyperplane depends upon the number of features. If the number of input features is 2, then the hyperplane is just a line. If it is 3, then the hyperplane becomes a two-dimensional plane. It becomes difficult to imagine when the number of features is beyond 3. SVM chooses the extreme points or vectors that help in creating the hyperplane. These extreme cases are called as support vectors, and hence algorithm is termed as support vector machine. How does SVM work? The basics of support vector machines and how it works are best understood with a simple example. Let's imagine we have two tags, red and blue, and our data has two features, x and y. We want a classifier which predicts the labels of new data point. If we plot our data points, it will look like this. This line is the hyperplane or decision boundary. Anything that falls to one side of it, we will classify as blue, and anything that falls to the other as red. This hyperplane acts as a separator. Now the question is how to choose the best hyperplane. Let's understand this scenario wise. If you look at this scenario, here we have three hyperplanes A, B and C. Now to identify the best hyperplane, we need to choose the one which segregates the two classes better. In this scenario, hyperplane B has excellently performed this job. Now in this scenario, we have three hyperplanes A, B and C and all are segregating the classes well. Now to identify the best hyperplane, we need to calculate the distance from the hyperplane to the nearest point, which is also called margin. The one with higher margin will be the best hyperplane. Here you can see that the margin for hyperplane C is high as compared to both A and B. Hence we name the right hyperplane as C. Another likely reason for selecting the hyperplane with higher margin is robustness. If we select a hyperplane having low margin, then there is a high chance of misclassification. Now I have a question for you. For this scenario, use the rules that were discussed in the previous scenarios and find the best hyperplane. Leave your answers in the comment section below. Let me see how many of you are predicted correct. I hope all of you predicted correctly, but some of you may have selected the hyperplane B as it has a high margin compared to A. But here is the catch. SVM selects the hyperplane which classifies the classes accurately prior to maximizing margin. Here hyperplane B has a classification error and A has classified all correctly. Therefore the right hyperplane is A. Now for this scenario, can we segregate into two classes? Pause the video and think about it. The answer is yes, we can segregate it with the hyperplane. Two circles at the other end is like an outlier for star class. The SVM algorithm has a feature to ignore outliers and find a hyperplane that has the maximum margin. Hence we can say SVM classification is robust to outliers. For this type of scenarios, we can't have linear hyperplane between the two classes because it is a non-linear data. SVM solves this type of problem by introducing additional feature. Here we will add a new feature, z equals to x square plus y square. Now if we plot the data points, it will be like this. Now we can draw hyperplane here. Now that since we are in a 3 dimensions, the hyperplane is a plane parallel to x-axis at a certain z. Now if we look at our hyperplane in the original input space, it looks like a circle. Remember that we don't need to add any feature manually to have a hyperplane. The SVM algorithm has a technique called kernel trick. SVM kernels. The SVM kernel is a function that takes low-dimensional input space and transforms it to a higher dimensional space. That is, it converts not separable problem to separable problem. It is mostly useful in non-linear separation problems. Simply put, it does some extremely complex data transformations, then finds out the process to separate the data based on the labels or outputs you have defined. A support vector machine in practice is always implemented by a kernel. The kernel trick helps to make a more accurate classifier. Now if we discuss the types of kernels in SVM, we have three types. Linear kernels. It can be used as a normal dot product between any two given observations. Polynomial kernel. It is a generalized form of linear kernel. It can distinguish nonlinear and curved input space as well. Radial basis function kernel or RBF kernel. It is commonly used in SVM classification. It can map the space in infinite dimensions. That is the advantage we have with RBF kernel. Pros and cons of SVM. Pros. It works really well with a clear margin of separation. It is effective in higher dimensional spaces. It is effective in cases where the number of dimensions is greater than the number of samples. It uses a subset of training points in a decision function, so it is also memory efficient. Cons. It doesn't perform well when we have large dataset because the required training time is higher. It also doesn't perform very well when the dataset has more noise, that is, target classes are overlapping. SVM doesn't directly provide probability estimates. These are calculated using an expensive 5-fold cross-validation. It is included in the related SVC method of Python scikit-learn library. Applications of SVM in real world. As we have seen, SVM depends on supervised learning algorithms. The aim of using SVM is to correctly classify unseen data. SVMs have a number of applications in several fields. Some common applications of SVM are face detection. SVM classify parts of image as face and non-face and create a square boundary around the face. Text and hypertext categorization. SVM allows text and hypertext categorization for both inductive and transitive models. They use training data to classify documents into different categories. It categorizes on the basis of the score generated and then compares with the threshold value. Classification of images. Use of SVMs provide better search accuracy for image classification. It provides better accuracy in comparison to the traditional query-based searching techniques. Bioinformatics. It includes protein classification and cancer classification. We use SVM for identifying the classification of genes, patients on the basis of genes, and other biological problems. Handwriting recognition. We use SVMs to recognize handwriting characters used widely.